Welcome back to the Introduction of MEMS series. I'm Chang. We have talked about processing, so right now it's time to touch upon other topics. Here we will be reviewing survival mechanics information, MEMS mechanics introduction. Here is a outline of this series. We started by giving an introduction about MEMS, and discussing semiconductor material, the chip industry, and facilities. Then we spent 3, 4 lectures talking about process, and now we're going to talk about mechanics. After that, we'll talk about transducers. Because microelectromechanical systems always involve some kind of mechanical elements, such as membranes or beams, understanding of mechanics in terms of the displacement versus force or intrinsic stress or stress generation is crucial. Let's talk about some basic principles of sensing and actuation. We're going to use a electrostatic capacitor plate as a force generation or sensing element. The parallel plate configuration creates a capacitor. It can be used for sensing, namely if we measure the capacitance when the plate is moved or displaced, we can use it as a sensor. Uh, on the reverse, if we apply a voltage across these two plates, we can generate a force. So you can use it either as a parallel plate or you can use it as a interdigited fingers, IDTs. The IDTs use the capacitors on the sidewall. We'll mostly be focusing on the parallel plate capacitor. So the parallel plate capacitor, the capacitance is equal to the stored charge divided by the voltage. Uh, we can rewrite it as epsilon times A divided by D as a first order approximation. Epsilon is the permittivity and D is the distance between the plate and A is the area of the capacitor. A good example of a parallel plate capacitor as a actuator is the Texas Instrument DLP, digital light processor. In this case, the mirror is one of the capacitor plate. It is suspended by a torsion hinge. The counter electrode is this anchor on the substrate. If you apply voltage across the anchor and the mirror, it can cause the uh, mirror to rotate one way or another. The equivalent electromechanical model is such that you have a uh, electric force created by a capacitor, and then it is counteracted by a mechanical force. The mechanical force is equal to the Km, which is a force constant, multiplied by the displacement, Km and x. So mechanical force is equal to Km times x. If you know the force and you know the Km, then you should be able to calculate the relative displacement. The key is how to calculate the Km. So we have uh, at least a number of configurations. Uh, in general, a mechanical beam is a supporting structure. It can be classified by the boundary conditions. This one, for example, is called a fixed free beam, meaning one end is free and the other end is totally fixed, is anchored. This one is called a fixed guided beam. Both ends are fixed, and this one is also fixed and guided. because the center cannot rotate. So it's fixed guided beams, but we have four of them in parallel. Here is a summary. The boundary conditions um, are fixed or guided as such or free. And you can calculate the number of degrees of freedom. The more degrees of freedom there is, the uh, more displacement can be created. Here are SEM examples of uh, fixed beam, fixed fixed free, and fixed free beams. This is an example of a fixed beam where the plate is guided in the center. The plate will likely not deform. Now, how do we calculate the beam displacement? If we apply a force, the amount of displacement is F divided by Km, or you can calculate the Km as F divided by X. When a beam is bent, a stress field is developed in the beam internally. We can calculate the stress field. Here is a diagram. Suppose we apply a torque of M to a beam, and it has a cross-sectional area as shown here, and a thickness from M to N. Using the torque balance equation, the total torque has to be equal to the maximum uh, stress, and you can estimate the stress as a linear distribution where the stress is zero in the center in the neutral axis. So you can integrate the stress multiplied by the area to counterbalance the M. From here, one can calculate the maximum uh, stress. The maximum stress happens on either the inner or outer surface, but no matter what, it is happening at the surface of the beam. If we have a fixed free beam as an example, the width is W and the thickness is T. The Young's modulus is the modulus of elasticity of the material. Young's modulus is basically a measure of how strong the atoms are bonded together internally. It's a atomic level uh, force constant. The moment of inertia of the beam is I equal to Wt cubed divided by 12 for a rectangular cross section. The maximum angular displacement is FL squared over 2EI, and the maximum vertical displacement is FL cubed over 3EI. From here, you know that the Km is F divided by the displacement, which is Young's modulus times width times thickness to the third power divided by 4 and L to the third power. You can also calculate the resonant frequency based on this. The modulus of elasticity is the maximum stress divided by the maximum strain at the atomic level. Here are the equations for fixed free beam, fixed guided, and fixed beams. You can apply a force at the end or in the middle and calculate the displacement. These are the formulas for calculating the force constant of different types of beams under different boundary conditions.